You know, we rely on straight lines for a lot of things. The more you work, the more you earn. The faster you drive, the sooner you get there. But what about the questions where the answer isn't a number on a line? What about when the answer is just a simple yes or no? Today we're going to jump from the comfort of straight line thinking into the really powerful world of nonlinear models. These are the tools built to give you those clear, logical answers.
So here's our game plan. First, we're going to see exactly where the good old straight line hits a wall. Then we'll look at the new framework we need for what's called attribute data. We'll do a real deep dive into the main workhorse, logistic regression, and then explore a couple of its specialist cousins, the logit and probit models. And to wrap it all up, we'll talk about how you make the final call on which tool to use.
So this is it. This is the big question we're tackling today. Just think about it for a second. Will a customer churn? Yes or no? Is this transaction fraudulent? Yes or no? Will this project succeed? Yes or no? These are all binary, black or white questions. And as you're about to see, trying to force a straight line to answer them, well, it leads to some pretty bizarre and flat-out wrong conclusions.
All right, first things first, let's talk about the limits of the tools we already know and love. Look, any great consultant knows their toolkit inside and out, and that includes knowing when a tool is going to break. For linear regression, that breaking point is when you're trying to predict a yes or a no.
Now, we're probably all on the same page with this one, right? Simple linear regression is foundational stuff. It's an awesome technique for drawing the best possible straight line through a bunch of data to predict something. It's elegant, it's intuitive, and it works perfectly as long as you're predicting something continuous.
And this gets right to the heart of the problem. Linear regression is a champ with continuous data, stuff that can be any value in a range, like temperature or price. But our yes-no questions? That's categorical data, or as it's often called, attribute data. So let's say we code no as a 0 and yes as a 1. What happens when our straight line model spits out a prediction of 1.5? Or even weirder, negative 0.2? What does that even mean? The answers are literally nonsense because the tool is trying to fit a line to something that can only ever be a 0 or a 1.
So here's the bottom line. This isn't just a friendly suggestion. This is a fundamental rule you just can't break. Using linear regression for this kind of yes-no data completely violates its core assumption. It's kind of like using a thermometer to measure distance. You'll get a number, sure, but it will be meaningless. You're using the wrong tool for the job.
Okay, so we've clearly defined the problem. Now for the fun part, the solution. It's time to build out a new framework, one designed from the ground up for these kinds of categorical questions.
So, say hello to nonlinear regression. Instead of trying to force our data into a straight line, these models work with it. They embrace the curve. They're specifically designed to map the relationship between what we know and the yes-no outcome we want to predict in a way that actually makes sense. The output isn't a weird number, it's a probability.
And within this framework, what's in our new toolkit? Well, we've got three main players we're going to get to know today. First is logistic regression. That's the most common one by far. Then you have its very close relatives, logit and probit analysis. They all tackle the same core problem, just with slightly different approaches.
All right, let's roll up our sleeves and do our first deep dive. We're going to start with the MVP, the one you'll see out in the wild most often, logistic regression. You could almost say this is the hero of our story today.
And this, right here, is why it's the hero. Instead of a straight line that can just shoot off to positive or negative infinity, logistic regression uses this beautiful S-shaped curve. It's technically called a sigmoid curve, but just look at it. See how it's naturally squeezed between 0 and 1? This is perfect. It means the output of our model can be read directly as a probability, the probability of getting a yes. No more weird predictions like 1.5 or negative 0.2. It's just clean, interpretable probabilities.
So how does this magic actually happen? Well, it's not really magic. It's a pretty straightforward four-step process. First, you just confirm your outcome is in fact categorical, a yes, no, true, false type of thing. Second, the model does this clever math trick called a logit transformation. Third, it fits that beautiful sigmoid S-curve to your data. And finally, the most important part, it takes the probability from that curve and makes a call, classifying the outcome as a 0 or a 1.
Let's make this concrete. This powerful example comes from the American Cancer Institute. We've got data showing how many cigarettes someone smokes a day and whether or not they develop throat cancer. The outcome, throat cancer, is a perfect binary variable. 0 for no, 1 for yes. This is exactly the kind of problem logistic regression was born to solve. So our mission, should we choose to accept it, is crystal clear. can we use the number of cigarettes per day to predict the probability that a person falls into that one category, meaning they developed cancer?
Okay, let's peek under the hood for a second. Now, don't let the formula scare you. The first step is to calculate this value called z. And if you look closely, this part actually looks a lot like our old friend linear regression, right? You've got your input, a coefficient, and a constant. So we crunch the numbers and we get a z-value of about 0.37. Think of this as our initial linear-style finding.
And now, here comes the transformation. We take that linear-ish z-value we just calculated, and we plug it into this sigmoid function. This is the engine that generates the S-curve. We run the calculation, and boom, we've turned that 0.37 into a meaningful probability of 0.59.
So we have our probability, 0.59. Now what do we do with it? We classify it. We set a decision boundary, a threshold, which is usually 0.5. Since our probability of 0.59 is higher than that 0.5 threshold, we classify this outcome as a 1, or yes. If it had been 0.49, we would have called it a 0, or no. And just like that, we've gone from raw data to a clear, actionable prediction.
Okay, so we've got a really solid handle on logistic regression now. Let's just zoom out a little bit and look at a couple of its close cousins that you might run into, the logit and probit models.
First up, the logit model. Now this is going to sound super familiar because a logit model is essentially just another name for the engine inside logistic regression. It's just a model designed for a categorical outcome that uses that same logistic S-curve we just saw. A classic example would be a doctor trying to predict patient mortality based on cholesterol levels, a textbook binary outcome.
And then there's the probit model. It's the other key player. It does the exact same thing, predicts a binary outcome. The only real difference is the math behind its S-curve. Instead of that logistic distribution, it uses the standard normal distribution. You probably know it as the basis for the classic bell curve. So a great example here might be predicting if someone gets into business school based on their GMAT score.
So you're probably thinking, okay, great. Logistic, logit, probit, they all sound pretty similar. Which one do I actually use? That's an excellent question. This last section is all about giving you that practical final takeaway.
The true statistical difference between them is really subtle. It all comes down to the shape of the S-curve at the very extremes. The logit model has slightly flatter tails, meaning it approaches 0 and 1 a little more gradually. The probit model has heavier tails, so it gets to 0 and 1 a little bit faster. Now this can matter for some really advanced statistical work, but for most day-to-day problems, the difference is tiny.
And that brings us to the single most important piece of advice from our research. For the vast majority of problems you will ever face, the choice between a logit and probit model just doesn't matter. They're going to give you almost identical answers. The real key isn't getting lost in which one to pick, it's remembering to use one of them in the first place instead of trying to use a straight line.
So, there you have it. We've gone from the hard limits of a straight line to the simple elegance of the S-curve. We've seen exactly how to take complex data and turn it into a clear, confident yes or no prediction. The final question, then, isn't for me, it's for you. What binary question, what yes or no problem in your world has just been waiting for the right tool to come along? Now you have it. So what are you going to solve?